Before there were weather satellites and sophisticated forecasting technology, clouds were the best way to predict what weather was coming. Clouds high up in the sky or no clouds at all meant fine weather, but clouds moving low in the sky or dark clouds meant rain was on its way. Common sayings even sprung up from our cloud observations, like red sky in the morning, sailor's warning, red sky at night, sailor's delight. And there are many more across time and different cultures. Today, geographers and meteorologists still rely on clouds to forecast the weather by studying how and why they form. Clouds give us important information on the temperature and amount of moisture in the atmosphere, which can help us predict weather from cloudless summer afternoons to overcast winter mornings. More than that, a map of the world's clouds tells us about today's energy flows and weather patterns. And unlocking the mysteries of clouds will help us better understand how the atmosphere is warmed. So today, we'll join countless peoples throughout history and look up at the clouds. I'm Hallie Zay Carrere, and this is Crash Course Geography. Clouds are often described with dramatic words like ethereal or ominous. They seem alive, born from the atmosphere, appearing as mysterious objects like UFOs. But clouds are also useful atmospheric data. Clouds are basically big water buckets floating in the atmosphere. They're composed of billions of so small they're invisible water droplets and ice crystals too small to form raindrops, so they stay suspended in the atmosphere. In fact, each cloud has its own anatomy, height, name, and reason for being. Kind of like an atmospheric person. Sailors of yore and scientists of today know that clouds can tell us more than whether it might rain. For example, we often see a villainous type of cloud hanging over cities called smog. A London physician first coined the word smog in 1900 to describe the combination of smoke and fog, the layer of cloud on the ground that cast a pall over the city. Smog is pollution that harms our lungs, irritates our eyes and throat, and even corrodes structures over long periods of time. It also traps extra heat in the atmosphere, contributing to human-caused global warming. But the presence or absence of clouds can make a big difference in the amount of energy that reaches the surface of the Earth, too. Let's go to the thought bubble to meet them. As modern storm chasers, we're ready to drive for hours to document unique cloud formations and send data back to local meteorologists. We have to know who we're dealing with, but luckily, the vast majority of clouds are classified into 3 types, based on the way they look. The first clouds we spot are wispy tendrils of white. These cirrus clouds, or mare's tails, are made up of ice crystals, and they only exist way high up above 6,000 meters. Cirrus clouds like these reflect 50% of insolation, or incoming solar radiation. But they're even better at trapping long-wave radiation trying to move back out to space, insulating and warming the Earth's atmosphere as part of the natural greenhouse effect. Miles down the road, the sky is filled with dull, gray, flat, horizontal layers of low-level clouds below 2,000 meters. Stratus clouds like these reflect and scatter about 90% of insolation, which cools the Earth by keeping incoming energy from reaching the ground. You can blame them for the dreary weather. We keep driving as the weather clears, but now we notice lumpy cumulus clouds taking over the sky. Cumulus clouds are signs the energy in the atmosphere is shifting around. Because they can be so thick and reach so far high up into the atmosphere, they generally reflect as much energy away from the Earth as they absorb to warm the Earth. So they're basically neutral in terms of warming the atmosphere. If we're lucky driving through this hot afternoon, we'll see the bright lumpy cumulus clouds keep growing higher and thicker. Now the rain is picking up and we've found our storm. The rain, or nimbus, form of cumulus clouds. Cumulonimbus clouds are towering rain clouds which showcase a powerhouse of energy exploding as big storms. Thanks, Thought Bubble. To climate scientists, understanding clouds and how energy flows through them is critical to understanding how our Earth warms and cools, and how climates change. While cirrus clouds only appear at high levels, stratus and cumulus clouds can appear at any level. And cloud names actually describe this. So just like people can be complex, we could have, say, lumpy cumulus clouds growing in the middle above 2,000 meters but below 6,000 meters at the alto level. These are called altocumulus. Or we could have horizontal stratus clouds way high above 6,000 meters, forming icy cirrostratus layers. Cirrus, or the prefix cirro, means high level, alto refers to the mid-level, and low-level clouds are just plain stratus or cumulus. Maybe with a nimbus tacked on if it's raining. But no matter where or what they are, clouds naturally cool and heat the lower atmosphere, though how much depends on the altitude, cloud type, amount of cloud cover, and thickness. Basically, if we imagine clouds as floating water buckets, each type holds different amounts of water. And clouds are just one phase of the hydrological cycle that circulates water between the atmosphere, the hydrosphere, the lithosphere, and the biosphere. Clouds tie the atmosphere and hydrosphere together, by the way. To form clouds, water has to enter the atmosphere through evaporation, which is when liquid water molecules absorb enough heat to become energized and break away from the surface as water vapor. The water vapor stores this extra energy as latent heat of evaporation. For a gram of liquid water to turn into water vapor, it absorbs 585 calories, which for us would be like eating 5 largish bananas. This is why when sweat evaporates from our bodies, it usually has a cooling effect. The liquid water absorbs some heat from our bodies and some water molecules turn into vapor. Humidity describes how much water vapor is in the air. In general, the air at high latitudes like the Arctic and the Antarctic is naturally colder because of less sunlight, so it has much less water vapor and is less humid. Places like the Caribbean or other tropical and equatorial regions of Earth have hotter air with more water vapor and more humidity. Because water vapor can store energy as latent heat of evaporation, humidity is linked to how much energy is available in the atmosphere to produce weather. So low humidity is part of why we don't usually hear about devastating weather events like hurricanes coming down from the Arctic. And we can sense humidity on a personal level because hair lengthens as humidity increases and contracts as humidity decreases. I know a thing or two about that. In weather reports on the news, when they talk about a warm front moving in and 55% humidity outside, back to you, Barbara, they're actually talking about relative humidity. Relative humidity is a comparison between the actual amount of water vapor in the air and how much could be in the air. When air at a certain temperature is at 100% relative humidity, it contains the maximum amount of water vapor possible. So it's saturated, like a sponge full of water that can't soak up any more unless you squeeze it out. Except squeezing water out of the atmosphere is rain. Any kind of humidity strongly depends on the air temperature and how much moisture is available. At higher temperatures, it's more likely that more liquid water molecules will have the energy to evaporate into water vapor and float around in the atmosphere. So in hotter areas, the air can hold more water. Of course, just because warm air can hold more water doesn't mean that there's always water vapor around. Inland regions like the Central Sahara Desert are very dry because they're far from the oceans and there's not a lot of liquid water available to be evaporated. But let's say we're staying in a cabin by a lake, so there's plenty of liquid water around. The same relative humidity can feel very different depending on the air temperature. On a hot day, 70% relative humidity can feel heavy, sticky, and uncomfortable, almost like standing in a cloud. Because the air can hold more total water, 70% of saturation is a lot of vapor. Plus, when we're hot, we sweat, and when there's a ton of moisture already in the air, our sweat can't evaporate as easily, so we're stuck feeling damp. On a cold day, 70% relative humidity is much more comfortable because the colder air can hold less water, so 70% of saturation isn't as much water vapor. Plus, it's cooler, so we don't need to sweat as much. Changing temperatures can also change the relative humidity even if the amount of moisture stays the same. Like during the day it might be sunny and hot and the relative humidity is only at 50%. But as the sun sets and temperatures drop at night, the air has a harder time holding onto the water vapor. By morning, it feels very damp and dewdrops form on the grass. We've reached 100% saturation, even though no extra water vapor was added to the air. During the night, we reached the dew point, which is the temperature when water vapor can condense back into liquid droplets, given the current amount of water vapor in the air, like as dew on the grass or fog, which is really just a cloud on the ground. So at the dew point, our metaphorical sponge would be full, and a cloud can be born. If we compare a dry region such as the Sahara Desert to a humid region such as Mississippi, it takes a lot more cooling to reach the dew point and get condensation in the desert than it does in Mississippi. Even though water vapor and liquid water are just two different arrangements of water molecules, it's nearly impossible for condensation to happen if there's no surface for a water droplet to cling to, like the outside of a cold soda can. So there's one key ingredient of clouds that we haven't mentioned yet: condensation nuclei. These are microscopic particles like sea salt spray, dust, smoke, pollen, and volcanic material in the atmosphere that provide a surface for condensation to take place. As trillions of our water molecules cling to specks of dust and form billions of tiny liquid water droplets, and sometimes freeze into ice crystals after that, we get a cloud. So I guess clouds are more like a big bucket of dusty water. The condensation phase of the hydrological cycle releases all the stored up energy in that water vapor. For every gram of water, 585 calories, or 5 largish bananas, are freed as the latent heat of condensation. So if a small puffy cumulus cloud holds 500 to 1,000 tons of moisture droplets, that's a tremendous amount of energy being released that can power a storm. Every cloud is really the result of cooling. We've only described in general how clouds form from water molecules being energized and evaporating before condensing into liquid droplets in the atmosphere. But so much more goes into creating the unique panoramas that fill the sky. Each cloud is one of a kind, just like even though we can generalize about how people are born and grow up, there are so many intricacies that make a person who they are. Even whether our cloud will be a small puffy cumulus cloud or an ominous cumulonimbus cloud depends on so many factors, like the specific temperature and humidity of the initial air and changing atmospheric conditions as our evaporated water molecules rise. And with 50% of the Earth covered by clouds at any given moment, there are so many possible shapes and sizes. It's no wonder clouds are such an ever-changing and beautiful aspect of our environment. All of these elements come together to deeply affect the Earth and us humans too. We've paid attention to clouds for thousands of years, not just because of their beauty, but because they absorb, scatter, and reflect rays from the sun, influence the global energy budget, and circulate the key ingredient for life around the globe. But more on that and raindrops next time.